Hey guys, we're going to be looking at conditional probability and two-way tables this time. So it's an extension of the conditional probability stuff that we were doing in the last video, but this time we're going to be using two-way tables to do it. Now two-way tables are useful to compare or list the two characteristics or the outcomes of two events, so like rolling two dice, which we'll do down here real quickly. So one characteristic is listed in the columns and the other characteristic is listed in the rows. And so it's useful to help us get a sample space of the outcomes that we are looking at when these two characteristics cross over, or we're looking at totals, which we'll do again a little bit later. So with our conditional probability, you're going to see the word given. I may not have addressed it, in fact I didn't address it last time. The word given is going to be used a lot to tell you what the condition is. This line that you'll see in the shorthand for our probabilities means given. So this is greater than 4 given that there's 1, 3. Instead of actually writing the word given. Now, if we are doing conditional probability, let's take a look at our first example here. We've got find the probability that the total of two 6-sided dice is more than 4, given that one of the dice shows a 3. So here's our given, shows that this part is our condition, which is why it's down here in my shorthand. We've got 2 dice, so it makes it perfect for a two-way table. We've got the outcomes for the first dice. We've got 1, 2, 3, 4, 5, and 6. And we've got the outcomes for the second dice. 1, 2, 3, 4, 5, and 6. So we are looking at the total, which means we are adding both the results of the dice. So we can get 2, 3, 4, 5, 6, and 7 when one of the dice shows a 1. With our conditional probability, this, as I've set up here, restricts the total to a subset of outcomes. If we were to look at this condition here, 1, 3, we're looking at all of these outcomes and all of these outcomes. We're not even bothering with the rest because they don't have 1, 3. So out of those outcomes, there is 11, not 12, because we don't want to count this crossover twice. Out of those 11 outcomes, how many of them are greater than 4? So greater than 4 means we've got 5, 6, 7, etc. It can't actually be 4. So just circle the events here. Not events, but elements. So we get 5, 6, 7, 8, or 9. Again, we don't want to count this 6 twice. There are 9 out of 11 ways to get a number that is greater than 4 when we already know that one of the dice shows 3. Now with our two-way tables, or another way to look at our conditional probability rather, is you might be looking at some sort of experiment and you're trying to see if the result of one thing has the effect of another. So my example here is, does smoking increase your chances of cancer? That's just one way that we could look at it. What we're going to do in our example is we're going to be looking at the probability, does having red hair have an effect on the probability of green eyes? Now we've got a set of results. We've got hair color, and I should have this up here. Eye color is our other characteristic. So we've got blonde, black, red, or brown hair. We've got brown, hazel, blue, green eyes. and we have surveyed or gotten results of 582 people here. And we're going to check, does the probability of green eyes change from the general population if we know that they have red hair? Now, in our two-way table, just to make sure that we know how to read this, where these two characteristics cross over, then this is the number of people. So this is a frequency two-way table instead of the sample space we had with our two dots back here. 15 people out of the 582 have hazel eyes and black hair, because that's where our two characteristics are crossing over. 74 people have both blue eyes and brown hair. Down here in our totals, we're adding up all the number of people that have brown hair. 220 people out of the number of people we've surveyed have brown hair. 205 have, brown eyes, blue eyes. On the other side, we've got across here is the total number of people that have brown hair. Okay, small mistake. Being able to read our two-way tables is going to be important because we need to make sure that we know which one of these totals is going to affect things. Our next example is going to show that. So, back to the question at hand, we're looking at the probability of green eyes. So, how many people have green eyes from here? Eye color, green. 64 people have green eyes out of the 582. And we might like to express this as a percentage. So let me just get the 64 out of 582. We have roughly 11%. And then we're looking at the probability of having green eyes given that they have red hair. So out of the people that have red hair, the condition, as I said earlier, restricts the total to a subset, the subset here being the number of people that have red hair. Green eyes is 14 out of those 71. Okay, so here is our subset, red hair. There's the total of people that have red hair, and we're looking at the number of people that have green eyes and red hair. So, what is this as a percentage? So we can compare this accurately. We've got 14 out of 71 times 100. It's almost 20%. Now, because there is this significant change between the probability of having green eyes in the general population to when you have red hair, then we can say that there's likely some sort of effect here, that red hair has some sort of effect on the probability of having green eyes. So as a conclusive statement, in our example here, we've had students with red hair are almost twice as likely to have green eyes, going from 11% to 20%. Now, the last thing that we're going to do is looking at percentage two-way tables. Two-way table, but it's either a percentage of the total, the number down here, the rows total, so we might do 16 out of 23 and then 7 out of 23, so each row would be 100%, or we could look at a percentage of the columns total, so we could do out of the number of males, 16 out of 66, or 28 out of 66, or 22 out of 66. Now that depends what the question's asking, or what condition that we're given that we're going to have to focus on these different totals in our two-way tables. Let's look at our example here. We've got different types of workers, blue, white, service workers, and then we've got our sex, male and female, and we have surveyed 130 people in total. We're trying to make this a percentage two-way table of the total. Right, so not of the row or columns, but of the total 130 here. So each number is going to be out of 130. So for example, this one here is going to be changed to a percentage, 16 out of 130, and we're going to multiply by 100. 16 out of 130 times by 100. So it's about 12.3%. Females, 7 out of 130 are both blue collar and female. So again, 7 out of 130 times by 100. We have 5.4%. And making sure you have your total in your two-way tables because they're going to be useful. We've got 23 out of 130 times by 100, which is going to be 17.7%. I'd recommend you pause the video at this point and see if we can work it out, or the rest of the percentages for this table here. 130 out of 130, everything should add up to 100%. If you choose to pause, alright, so with our percentage two-way tables, this is what we should have gotten. 12.3% are male blue-collar workers, whereas 5.4% are blue-collar female workers. And we get our total percentages. Now, depending what total that we're looking at, it's going to change our questions here. We're looking at the probability of being female and a white-collar worker. So we could look at this from our percentage two-way table, or we could look at this from the table that we had above here. Out of the 130 people surveyed, to be female and white collar, there are 25 out of the 130 people, and we should have already worked out that that percentage is 19.2. But when we're given our condition here, I'll try to keep that table in frame. We've got our condition of being white collar, then this changes the total. So out of 53, then how many of them are women? We've got 25 out of 53. And we could look at this with the percentages if we wanted to. We could say that out of the 40.8%, that 19.2% are both a woman and a white-collar worker. And again, I'm cutting that upper table out of the frame, so we're looking right at the bottom of the video here. So, sorry, before I move on, that 53 again comes from the total from our condition here. That's where I was. White collar and a woman, So how many women are there that we have surveyed? We're looking 64 females, and out of the females, how many of them are also a white collar worker? Again, 25. So depending how the question is phrased, that's what I was going to try and say before, the total has changed out of 130, and then a different condition gives us out as 53, and then a different condition gives us out as 64. So we need to pay attention. And then just in case for the percentages, to be a woman, there is 49.2% out of the white collar workers. Again, 19.2%. Now, because these percentages are rounded, if you were to work out both of these answers, you might find that there's a small error. Otherwise, that should prepare us a bit. Good luck.